Hello, everyone. Welcome to this lecture of computer system security. Today, we are going to talk about hash functions and the application of hash functions. We first define what are the hash functions, and we talk about the properties that we expect to see from a hash function. And then we talk about types of hash functions. In general, we have two types of hash functions: keyed hash functions and unkeyed hash function. We'll talk about them. And then we talk about one very important application of hash functions, which is message authentication. And finally, I introduce some of the noun hash functions, and we go to details of only one of them. Because of course there are many hash functions and we don't have time to go over details of each of them. We just look at the one MD5, and that should be enough for our to get to understand how hash functions work. Of course, details for other hash functions that we just named them are different, but that should be enough for our course. Okay, let's get started and define a hash function. A hash function that we mostly show it as a function h like this is a function or algorithm that maps input message m of any arbitrary length to a fixed length output or bit string. Of course, in both m, which is the input, and the output, which we call it h of m, both of them are binary sequences or strings of binary values. Or if you look at them as a hex, we can also show them as a hex numbers, or we can also represent them as ASCII. But at the end of the day, they're both inputs are and outputs of a hash function are binary numbers. We just represent them differently. We may represent in binary. If we go in binary, we end up, for example, showing showing a sequence of 128 bits. Or if we make it in hex, it's going to be 128/8, or ASCII. Sorry, in hex it's going to be 128/4, or in ASCII it's going to be 128/8, and just the representation is different. But at the end of the day, we are talking about an information of 128 bits. Okay, the one important property that here we are talking is the message m might have different lengths. As you see here, m1 is shorter, m2 is longer, and when both they are fed into the hash function, to the same hash function, we get the same output. The output of hm is n bits. Output of hm2 is n bits, although m2 is longer, and also the output of m1 is n bits, while we know that m1 is shorter than m2. And this is a great property that we have for hash functions, because you know, when we want to somehow protect some part of our information, that might be the data or the information might be short or long. Sometimes it's a file in the order of a few hundred bytes, or maybe some kilobytes, or it might be even some megabytes or tens of megabytes. So the size might be different, and per that, the information that we want to protect might be different. But here, when we apply the hash function, we get the same size. We show it like this mathematically. We say h is a function from 0, 1 to the power of a star, which means that we don't know how many bits the input has, and it maps this space 0, 1 to the power of a star to a space of 0, 1 to the power of n. And of course, when we say 0, 1 to the power of n, it means all vectors of n bits at which every position is either 0 or 1, 0 or 1. So because you know this is a Cartesian multiplication. When you multiply 0, 1 to another set of 0, 1, what you get is this. You get 0, 0, 0, 1, and 1 and 0, and 1 and 1. These are all kind of pairs that we get after multiplication of set 0, 1 into itself. If we multiply to another 0, 1, the pairs become triples. Triples that order is important in them, and the number instead of 4 is going to be 8. So when we say 0, 1 to the power of n, it means that we have 2 to the power of n vectors of 0 and 1. Okay, of course, from the kind of different properties that we know for functions, I'm sure that all of you know this, but I just want to quickly review that. When we define a function, we are talking about two sets. Let's say, for example, set A and set B. Sometimes we call the set A as domain, and set B is defined as codomain. And of course, we have some element in set A. In our case, they're all vectors of 0 and 1, but it might be anything. For example, it might be a square, I don't know, triangle, star, C, whatever. And the function maps every element to one element, not more, in the set B, which is codomain. So here in the hash function, we are saying that the domain may have any size, but the codomain, it has only 2 to the power of n elements, not more. So we have elements from 0 all the way to the element number 2 to the power of n minus 1. So if the input space or set A or domain has more elements, let's say it has 2 to the power of n plus 1, we only have 2 elements, 1 elements more than codomain. So at least 2 of the elements in the domain have to be mapped onto the same thing on the codomain. So for example, A and a square, they have to map onto the same thing. So if that's the case, if that happens, that of course in the hash function it happens, because we are saying that our messages are from 2 to the power of m, while the output or codomain is 2 to the power of n, and most of the time n is smaller than m, we would find input messages that they should be mapped into the same hashed value. These elements or these input messages or input text that they are going to be mapped to the same hash function, they are called pre-image. They're pre-image of each other. So in the example I just drew, A and square, they make a subset of character A or element A and element square. If we define them as a set, this set is going to be a subset of the domain, which we called it A, and we call this subset a pre-image subset, because these two elements are going to be mapped into the same thing. That's why we call them pre-image. Anyway, by this type of refresh or introduction I said, we are sure about the hash functions that we would have pre-image sets or multiple sets of pre-image for the hash function. That thing is called in the hash, it is called collision. Collision, we define it this way. We say collision means that two different input messages are going to be mapped to the same hashed value, or they generate the same hash value. The hash function, when we input them to the hash function, we get the same output. That's called collision. Of course, from the security standpoint, we want to minimize the number of collisions, or we want to reduce it as much as possible. But from the math point of view, we know that it's impossible. We know that it's impossible because it's a basic math. 2 to the power of m is bigger than 2 to the power of n. So you will end up having to have some pre-images. Okay, but one property that we like to see in our hash function, based on the fact that we said we of course would have some collisions in a hash function, we like to see this property that finding collisions is not easy. I have a hash function. I know that there are some collisions in this hash function. Okay, yeah, but it shouldn't be easy for attacker to find hash function, because otherwise it's going to be very easy for the attacker to use the collisions against the security of the system. So if we just try to make finding the collisions, you remember we talked about conditional security. Conditional security says you are hiding something from me, you try to keep it secret, and of course you can't make it forever, because your system is conditionally secure, not purely secure. So there are some time instant of time that if I keep trying, I would be able to break and find your secret. But I should look at the cost that it imposes on me versus the value of that secret that you have kept it hidden. Okay, this is again the same thing. We know that collisions will occur in hash functions, but we want to make sure that it is not easy for the attacker to find them. It is for the attacker, it costs more than the value of the secret information to find and exploit collisions of a hash function. Okay, other properties that we expect to see in hash functions are this: ease of computation. Hash functions should be very easy in terms of computation because we want to use them multiple times. So it shouldn't be very complicated in terms of computation. If they're easy, it means that they can be used everywhere and they are not consuming a lot of energy. Because at the end of the day, many of our information that we need to and we like to keep them secret, they are on non-general computers. For example, you have your smartphone, or you have other devices which are even in terms of computational power, they're weaker than smartphone, but we still want to keep our data secret. All the components and devices that you have, and they are get connected to internet of thing, or IoT devices. In terms of computation power and energy, they're very weak, but still they work with our personal data. So we like to keep our data safe and secure, but they don't have that energy and power that a normal computer has. So the hash functions, if we keep them simple or computationally easy to compute, it means that they need not much energy for being computed, which is good. And of course, if they are simple, it means that they can be calculated, or they can be processed very fast. Okay, there are three other properties that these are kind of system level properties. We have three kind of other properties that point to the hash function itself. The first property is called one-way property, or pre-image resistance, which means that for a hash function like h, if I know the output, if I'm an attacker and one specific output of that hash function is given to me, you say that, okay, this is 128 bits of value, which is the output of a hash function x, and I'm an attacker. It should be very computationally difficult or infeasible for the attacker to find or to drive the input m that has generated this output. So given the output y and the hash function h, it should computationally be feasible for the attacker to find a message m such that hash of that message m is y. Because this is basically the reversing of the hash function. If you give me something hash and I can easily find what was the original message, it means that I'm breaking the hash function. So computationally should be infeasible. When we say computationally infeasible, it means that, for example, it should be, if I want to do brute force, it should be 2 to the power of a big number, 128, for example, which is the thing that most of hash functions do. Okay, the second property, which we call it second pre-image resistance, it says if you give me a message M1, given a message M1, it should be computationally infeasible to find another message M2 such that the hash function of M1 and M2 are equal. You give me a message in one, and we all know the hash function. You remember kind of regarding to the open source design in the security, we don't want to keep the detail of the algorithm. It might be encryption algorithm or hash algorithm. We don't want to keep that details secret. Keeping that secret is not going to help us. So everybody knows the hash function. For example, when we say MD5, everybody can go on internet and easily find the algorithm of MD5 and details of MD5, or SHA1. Everybody can go. So the detail of algorithm is there. Everybody knows that. You give me a message M1. I know the hash function. I can hash it and find the hash of that message M1. It shouldn't be easy for me to find message M2 so that M2 also generates the same hash function. It should be computationally infeasible or very costly for me. And this is the definition of pre-merge that I just talked about in the previous slide. It says for a given function, a set of elements that that in the domain that which are being mapped into the given subset on the codomain. Okay, this is the second property we call second pre-merge resistance, and the third property that sometimes it is called strong collision resistance. It says that it should be computationally feasible to find any two distinct inputs that they generate the same hash values. So here, the attacker is kind of allowed. The attacker just knows the name of algorithm, hash function MD5. Okay, attacker goes on itself and tries to find at least two messages M1 and M2 that they produce the same hash value. If the attacker can find that, that can be published as a paper. That's a research. And for many of these algorithms that I will be talking only about MD5, but I point to MD5, SHA1, that sometimes they call it SHA1, SHA2. If you go online, you see that the first person who broken them, the first person who could find a collision in them has published a paper, and that paper kind of was welcomed by the community because they realized that, okay, SHA1 is no longer kind of protected. People found some collisions in that. Okay, now the next topic that I'm going to, the next thing that we should know about hash functions is the type of hash functions. In general, we have two types of hash functions: unkeyed hash functions and keyed hash functions. The name, I would say, is kind of clear and gives you the idea. In unkeyed hash functions, there is no key. Hash function, it just takes the message M1 and then applies the function, whatever the function is, and gives you the hash value, which is, for example, let's assume it is 128 bits. That's it. But in keyed hash function, there is also a key that should be, of course, somehow shared between the sender and receiver, or the person who is hashing the information and the person who wants to use that hashing. One important feature about hash functions is that they're one-way functions. Hash functions are non-one-way function. What that means is, it means that once you hash a message like M1 into, for example, some hash, let's say h of M1, M1 is h of M1 is supposed to be not related to M1. It means that there is no algorithmic way for you to return from HM1 to M1, which is pretty much the first feature I just talked about it. So given that said, when we say there is a key and the key is used by the sender and receiver, later in this lecture, I'll explain that sender and receiver, it doesn't mean that the receiver wants to use the key in order to unhash. No, there is no unhash, or there is no reverse way for a hashed value. But we'll see that a hash function can be used at by two parties at the sender and receiver side for example, authentication. Anyway, this is we'll see the detail of the uh, um, how to use key and unkeyed hash functions for authentication. But let's talk about keyed hash functions. In a keyed hash function, like the name implies, there are some keys which are being used in the hash kind of procedure. They should be easy for computation, and given M, which is the message, and K, we can easily compute hash of K and M. And key non-recovery feature, it says that it should be computationally infeasible to recover the secret key given one or more text hash pairs. For example, I know that message MI, when I hash it, it returns something to me. This is the input, let's say 200 bits. I hash this and I get something 128. Looking at these two, comparing these two, or any number of these such pair, it shouldn't be computationally easy for me to extract, to drive the key, because the key should be if the attacker finds the key, it would be easy for them to kind of impersonate to the system, to play the role of the sender. Okay, this is a property that we like to see for keyed hash functions. Okay, let's talk about the applications of hash functions. Where are we using hash functions? For encryption algorithms that we talked in the previous sessions, it's somehow easy to see what's the application. We have some information and we want to keep that information secret. And of course, we encrypt the information and we save it somewhere, or we send it over the net. And at the other side, or when we want to retrieve that information, we of course decrypt that and we use it. And this way, we protect against any attack that address or alter the confidentiality, or we attain the confidentiality for our data. But what are the applications of hash functions, given that hash functions are one-way functions? You hash information, you get something, and that thing, there is no way from that information to return or retrieve to the original data. So what's the application? Here are some of the applications, some of the most important, that we will be talking about one of them in details, but I explained the two other as well. Okay, the first application that I'm going to talk about is password protection. Passwords are, of course, one of the kind of most well-known ways for authentication. You have username or user ID and a password. And in order to get some services, in order to access some assets, suppose you're asked to log in, and you're asked to give or enter your username and password. But is it against the security if I enter my password and my password goes to the server as is? First of all, there are some, of course, if we are talking about some remote access, accessing something over the net, or over the internet, I'm on one computer and I'm entering my username and password here, and the password is supposed to go over some routers and then eventually reaches to a web server or somewhere. So first of all, there might be some attacks, some kind of vulnerabilities against the password when it's being passed over the internet. So the password might be altered or might be revealed to some attackers over the internet. That's first kind of threat. The second threat is the server itself. Even if we assume that the network is protected, or we do something for the network. Let's say, for example, you say, I encrypt my password and I send the encrypted version. Okay, at the end of the day, the server is supposed to check your password. The server wants to, we designed this system in order to give access to only authorized persons or individuals. So the server should be able to check the password. So if we encrypt the password for protecting it while the password is kind of transmitting over the network, the server should be able to decrypt that password in order to check it with the correct passwords. And then after if the password is correct, server of course allows me to use that asset or use that service. But this is again against the security, because the server is also not supposed to access to our or get our password as a plain text, or be able to decrypt and get the password as plain text. So what we do, we use hash functions here. We have a dictionary of password, of course, at the server side. It says user 1, user 2, but at the password side, instead of storing password 1, password 2, which is of course something not good, we store hash of password 1, hash of password 1, hash of password 2, and so on. And this way the server never knows, the server side never knows what's your exact password. They only know the hash function of hash value of your password. And what you do, the moment you enter your password, user and password in your computer, in your side at your computer, the password value is being hashed. Have you ever noticed when you enter a password in, for example, many of the things, for example, when you want to log in into your ANT email, you enter username and then password and then click it. In some sites, you see that the username is just is, but the password, the length of password increases. You have entered, for example, 10 characters, but after you hit the login button or after you hit the enter, it becomes, for example, something very long, 20, 100 characters. That's why, because the password is not being sent as a password or as an encrypted version of the password. No, hashed of the password is going to be sent to the server. So this way, the server never knows your password. First, your password is going to be securely traversed over the network, and no one realizes what's your password, except yourself, of course. And this way we can protect our password from being transmitted. So one major application of hash functions is password protection. So even if the attacker gets a copy of that, for example, as an attacker may sniff the network, it gets something which is a hashed value, and for them it's not possible to kind of reverse that. The second application that I'm going to talk about is called key derivation. Key derivation means that we have something called session key. Anytime that we want to start a secure transmission, there is a session. We call a session, and that session kind of is valid for a limited amount of time. Once that time kind of is over, you need to create a new session, and the session keys are being generated from using hash function. So that's again something. For example, you of course, I'm sure that you noticed that you go into some site, for example, your bank account. If you don't do anything, after some minutes, your session will expire, and you need to renew your session. That session key is being created using hash function. And the last application that I'm going to talk about it in more details is message authentication. Message authentication means that you use hash functions, or we call the hashed value, we call it also message digest. Message digest, or something like a fingerprint of your message, you append that into the original message in order to authenticate the message. Who has sent this message? Is that message correct or not? Okay. Okay, so in the rest of kind of for a few slides, maybe for the next 3 slides, I'm going to talk about the message authentication and the features that we expect to see. And then once I finish with that, I talk about few hash functions. Like I said, we just name them, and I only talk about one of them. We don't see the details of many of them. But this application message authentication is very important. So message authentication is kind of supposed to verify if a received message is authentic. What does that mean? It means that we want to make sure that the content is not altered. The content is the thing that the sender has sent. In fact, our data integrity was attained or not changed. The data is not changed. Second, more important thing, we want to make sure that who has sent this data. Is the person or the individual or computer who has sent this data is A or B, sender A or sender B. We want to make sure. And third, if there are some time kind of labels or sequence numbers, is this message carrying on the right sequence number? Is this message, for example, this I have received message number 1, and now I'm waiting for message number 2, and I received the message. Is this message number 2 that I received or not? You may wonder how this may happen. This may easily happen over the internet because our packets that we are generating them one after each other in our side, they may take different paths. And one of them may, for example, packet number 3 may find a path, may take a path which is less congested than the other path and may end up arriving at destination earlier than message number 2. So message 2 was generated at some point, message 3 was generated after 2, message 2 goes and received to the server before message 2. This is why we need to somehow make sure that at the server, I'm waiting for message number 2 and I have received something. Is this really message number 2? Is it the second part of information or not? So that's why this makes sense. Okay, you may wonder why encryption is not able to help us. Encryption is not able to help us because once we encrypt some information, we can just make sure that the information is kept confidential. We cannot make sure who has encrypted that the data. We can't. Encryption doesn't give us that information. So DES, AES, or other encryptions, they cannot help for encryption. Sorry, for authentication. That's why we see the combination of authentication and encryption most of the time, that we append something to the message, to the original message, and then we encrypt it using some key in order to attain both confidentiality and authenticity. Okay, and also there are some situations, interestingly, there are some situations at which we only need to attain the authentication. We don't need the confidentiality. Okay, here are some examples. Assume that there are a number of applications in which the same message is being broadcasted to a number of applications. When we say a same message is being broadcasted, it means that the message is already encrypted, or message may not need to be even encrypted. But in broadcast, when we say broadcast, it means that computer A, which is generator of that, it passes it to computer B. B receives, take a copy, and then B is supposed to send it to another one, because this is a broadcast. Everybody should receive a copy of that message. And B also send it to someone else as well, maybe to D, and so on. Everybody keeps doing that. So C receives a copy of that message. The message is not that important to apply, for example, encryption on that. But C wants to know who has sent that. C received that information from B. So C cannot just say that, okay, I received this from B, so B is the initiator, B is the generator. So there should be a mechanism that C wants to securely ensure that who has generated that message. So authentication can help here. Or the second situation is this: you have an exchange of information at which one side is heavily loaded. For example, you have a server and many other kind of clients are getting connected to that for sending some information or for receiving some information. The server cannot afford here, the server cannot here afford processing of complicated encryption algorithms, because basically there are many clients that they are communicating with the server. So in that case, the server just wants to make sure that who has sent that information, and that's it. So here again, we don't need encryption, we just need authentication. Okay, I'm going to talk about three basic mechanisms that we can do message authentication. One of them is message authentication code, or MAC. Also, people call it MAC, at which we do something like this. Suppose that we have two sides: server side that I just showed it by S, and receiver side that I just showed it by R. And this is the message. The message which is supposed to be sent, we define some function, some computationally complex functions, and we call it MAC function or MAC algorithm. This MAC function, of course, takes a key and produces something out of this message. And then we append that MAC thing to the main message and send it to the receiver. At the receiver side, the receiver performs the same thing. Divide the content of the message, generates a MAC. Of course, they have a pre-shared key. Generate the MAC and compares the MAC that the receiver has generated against the MAC that sender has sent. If these two match, it means that okay, this message came from sender, let's say Alice, and receiver makes sure that okay, this is a legit, this is a valid sender, and can use that information. Otherwise, if they don't match, it means that this information is not from, although it's somewhere here it mentioned that Alice has generated this information, but Max, they don't match, so this is not something from Alice, this is something from an attacker, and of course the receiver discard that. Okay, using this MAC, which of course is relying on this function, MAC function, the R receiver can ensure that the message has been sent from, the message has not been altered, because if the message is altered, a different MAC will be generated, and the attacker, we are supposing the attacker does not know the key. Secondly, the receiver can ensure that who has sent this message. And thirdly, if the message has any sequence number, the receiver or R can make sure that this is the right sequence, this is the right part of information that I'm waiting for. Or let's put it this way, the receiver receives them, and receiver can then eventually sort the information, the piece of information, in a correct way. It first puts 1 and then puts 2 and then 3. Although 3 may have received before 2, but the receiver will be able to reorder them or put them in the right order. So this is MAC. This is message authentication using MAC functions. Okay, now I want to here mention that it should be kind of easy for you to get this, that okay, instead of this MAC function that there are some functions that they call MAC function. Instead of this MAC function, we can of course use hash function as well, because we don't want to that MAC value to reverse that. We just want to use it as a for some comparison. So we should be able to use hash function for message authentication. Yeah, that's right. we have two types of message identification using unkeyed and using keyed hash functions. Of course, the first one, which is the easier, is message authentication using unkeyed hash function. The way it works is this. You want to send a message from A to B. The message, you get the message, you hash the message using a noun hash function, and you encrypt it using a key. You encrypt it using a key. And the key, of course, is something pre-shared between the sender and receiver. In parentheses, before continuing that, I'm just want to talk about this, that when I say the key is pre-shared, you may ask, because I have received one or two emails of you that you have asked, how are we supposed to distribute a key before start of a communication. We will be talking about it. I have mentioned to that, but just as a short answer, we have asymmetric encryption algorithm at which we can produce and generate these pre-shared keys. So there are ways for that. We will, after the break, the week after break, we will be talking about them. So when I say pre-shared key, there are ways to do that. Okay, I'm closing the parentheses and I'm getting back to the discussion. Sorry for that interruption. So I was telling that, yeah, we generate the hash value for that message, for the message. And of course, it's gonna be something. We encrypt that using a pre-shared key, we get something, and we append that encrypted hash value into the main message. This is encrypted hash value. And we send this. In the receiver side, receiver generates the hash value and decrypt this part using the key, using the shared key, and then compare. If the comparison goes through, it means that, okay, this is a message from the sender, which is being claimed in the message. If the message says that I'm from Alice or I'm from this IP address, yeah, right, this is from that IP address, because that IP address is the only person or the only individual that has the key. I shared that key with only that IP address or that person. And if that it doesn't match, it means that either the message was tampered, somewhere message was is not correct, or something goes wrong in the message, or the sender, the claim sender, is not the real sender. So advantages of using this approach over encrypting the entire message, is this. Sometimes, of course, we save time because encryption software are way more complicated than hash functions. So we just encrypt a small portion, which is the hash value, not the whole message. That's one thing. And you may say that, okay, we may use encryption hardware. Yeah, encryption hardware are sometimes not that expensive. We can buy them, but the thing is, they are good for or they performance gain returns if you want to encrypt a big amount of data. If you want to encrypt a small amount of data, it's better not to use them, because this kind of money we spent is not going to be returned. Yeah, that's and encryption, like I said, and they are optimized for a large amount of data. Yeah, and if you want to use the encryption for every node in your network, you may end up having to buy multiple encryption hardware or many encryption hardware, because you have many nodes in the network. And that way, of course, the price for a single one is not that expensive, but you may end up having to buy many of them, which impose a big kind of cost to us. Yeah, and finally, here I'm going to talk about the message authentication using keyed hash function. This kind of figure shows it very perfectly. Here we get the message, and we want to kind of create a MAC, message authentication code. what we do is that we apply the hash key, we append the hash key at the start and at the end of the message as a prefix and suffix of the message. And then we get the whole thing and then send it to hash function. We get the hash value. That hash value is being appended to the message part only. And we do, of course, we don't send the keys. We keep the keys at the sender side. We send it. The receiver performs the same thing. Appends the key of the hash, which is the encryption key is pre-shared. The key has already shared before between the sender and receiver. So it applies, the sender applies its own key, which is supposed to be the same, equal to this key. It makes this and send this to hash, get the hash value and compares it against the hash value received from the sender. If they match, it means that the message is authentic and the message has come from the sender who has claimed. Otherwise, it is not authentic. And this is a message authentication using hash function. Okay, now that we have talked about message authentication and other applications of hash functions, now let's talk about the hash functions themselves. We have many of them. MD5 is one hash function that we know. For example, SHA1, SHA2, there are other hash functions that we know. I'm going to just talk about one of them because, of course, if you want to go to details, it's going to be multiple weeks only for the hash functions. MD5 is one of the hash functions which was kind of widely used. In 2004, a collision has found and was reported by some researcher, these two persons, Wang and Yu. And how it works, it consists of 64 operations. 64 operation. Here, what you see here is one operation. And these 64 operations are grouped into 4 rounds, and each round has 16 operations in it. And it generates output of 128 bits. And the input can be any size, of course, but the way it works between different rounds, it kind of defines some 128 bits of input. That this 128 this is one operation. You get to repeat 4 of these operations. Each one take 32 bits. The second operation gets another 32, and another 32 bit. And this way you make it 128 for the main algorithm. So what I'm saying is that the input data can be any size, but the algorithm breaks it down into data of a fixed length, 128, and then apply the hash functions on the first portion, second portion or second block, third block, and so on. And then eventually it returns you only 128 bits. If the data that, if the message that we want to kind of calculate this hash, it's not a coefficient of 128, the hash function appends some zeros to make it. Okay, and here is kind of the operation that we see, the one of the operations that we see in the hash function. It consists of 4 8-bit values, 32 bits, A, B, C, D. A, B, C, D are initialized to a constant value, to a certain value in the hash function based on this MD5. And here is the message. 4 bytes of the message come, and this 4 byte is being kind of used in a function. These 4 bytes you see here, D comes, 1 byte from the message also comes. D goes directly to A. This is the input of the round, and this is the output of the round. Input, let me write it here. This is the input of the round, and this is the output of that round. D goes directly to A, C goes to D, B goes to C, and B is defined as a kind of series of operation. It uses a function which is called the nonlinear function, of course, non-reversible, and some additions. These are modulo 2 additions. So you get let me clear stuff and then yeah, you get B and C and D, you send them to a function f, and here for example function f, which is not of B and D or B and C. This is a logical function. These are logical operation, bitwise operations, X or and or and not. This is X or, this is and, this is or, and this is not. Anyway, it takes a non-reversible or nonlinear function, generates something out of B, C, D, adds it to A. This operator is add, adds it to message, to 1 byte of message, and then a constant is going to be added, which is different. That constant key is different for each round of the hash, and then it's being shifted to left. Sorry, it's being rotated to left to some bits, to some bit space, and then again it's being added to B, and what you get as a result, it goes to byte B. So you see that it's a function of input, which is, of course, there is no way for returning from this side to this side. And we don't need, because they are not supposed to be reversible. We just want to generate something out of the input. And this is called MD5. I just wanted to give you some idea how a hash function works. Other hash functions that you may heard about them, SHA1, sometimes people call it SHA1. It has the output of 160 bits, 20 bytes. And in 2017, a collision has found for that. SHA2 that generate output of 224, 256, 384, and 512 bits. And it's being used in many applications. Although all of them, all these three that I just talked about them, MD5, SHA1, and SHA2, they're broken, but they still are being used in many applications. Because the collision being found, it doesn't mean that it is easy. It means that someone was capable of breaking it, but it doesn't mean that it's very simple and easy for everyone. So there are even now still being used. Okay, we are done. Please use SHA2 as an attendance code for today's class.